In chapter 3 of the book, we cover vector algebra. As we know, vector is a quantity that has both magnitude and direction. And in this lecture, we're going to review a few of the methods that we use to add, subtract, multiply, divide, etc. Using vectors. This is vector algebra. Just a quick recap of what we've already covered in chapter 1, I believe it was. Graphic techniques for adding and subtracting vectors. If you have two vectors E and D, as shown here in picture in figure A, then what is D plus E? Well, there are two different ways of figuring that out. One is the tip to tail rule, where you add vector E to the tip of vector D, and then the vector formed by drawing a vector from the tail of the first, or the tail of D to the tip of E, is the sum, D plus E, and I use two little arrows on top of each letter to indicate that both D and E are vector quantities. Alternatively, you can use the parallelogram technique, where you form a parallelogram by drawing a parallel line from the tip of E parallel to D, and from tip of D parallel to E. Then the long diagonal is the sum of the two vectors, and the diagonal from the tip of D to tip of E is E minus D vector, and this diagonal from tip of D to E, of course, is D minus E. So this is the parallelogram technique for adding and subtracting two vector quantities. Let me also mention a quick mention of the Pythagorean theorem. If you have a right angle triangle with sides ABC, where C is the hypotenuse, then C squared is equal to A squared plus B squared, as shown here. And the angle theta, sine theta, is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse, or B over C. And tan theta is opposite over adjacent, A over B. Now, if you do not have a right angle triangle, here we have a triangle with sides A, B, and C, and let's say we have an angle 45 degrees between the sides A and B. Then the cosine, you use the cosines rule to determine side C. C squared is equal to A squared plus B squared minus 2AB cosine of 45 degrees. If this angle here were, of course, a different, let me just use psi, so rather than 45 it have psi. This is a generic way to show it. Of course, I don't want you to think that it only works with a 45-degree angle. You can also apply the cosines rule, for example, for this angle phi, where the opposite side is B, therefore B squared is equal to A squared plus C squared minus 2AC cosine of phi. Notice that the angle of interest now is phi, and the opposite side here is B. Or in other words, phi is equal to inverse cosine of A squared plus C squared minus B squared over 2AC. Just a recap of some trig identities before we get started. Now, multiplying a vector by a scalar quantity, let's say here we have a vector A. It has some magnitude A units. If we now multiply vector A by, let's say, 2, okay, such that we get a new vector b, right? And what happens, vector b will have a magnitude twice as long as vector a, but it will point in the same direction as vector a does. So multiplying a vector by a scalar does not change a vector's direction, it only affects its magnitude. So if I were to multiply my vector a by 3, then the direction of a remains the same, however its magnitude increases by whatever multiple that we have. So it's important to remember this, because as we saw in the earlier chapters, for example, velocity was change in position divided by the time interval. Velocity is a vector, change in position or displacement is a vector, whereas time is a scalar. Now this means that the direction of the velocity vector is the same as that of displacement. Similarly, acceleration is change in velocity divided by change in time, which means that acceleration and change in velocity have the same direction, because in both cases we divide the vectors, respective vectors, by scalar time. Okay. Now what happens when you multiply a vector by -1? If you multiply a vector by a minus, the magnitude, which is the size of vector, remains unaltered. However, the direction of the vector switches. It turns around 180 degrees. So here we have vector a, which is described by some magnitude a and the direction of a. And if we were to generate to write down minus a would still have the same magnitude a, but its direction would be opposite to that of a. So if you have ducks flying at 5 meters per second in the southeasterly direction, and the velocity vector for the ducks, let's say, is given by v, then minus v would still be 5 meters per second, but in the opposite direction, which is northwesterly direction. So that's multiplying vectors by a scalar and generating a negative vector. So here I have 3 vectors. So if we like to, for example, we have vector a. If you multiply vector a by a scalar 2, you end up with 2a. 2a is pointing in the same direction as a, but has twice its magnitude. Now if you were to multiply a by -3, then we end up with -3a. Notice that this vector is now pointing in directly the opposite direction, and it has a magnitude which is 3 times that of the original vector. So very simple to multiply vectors by scalars. And you can make use of this in adding or subtracting, rather, subtracting vectors using either the parallelogram or the tip-to-tail technique. So if you're trying to calculate what vector p minus q is, then you can calculate p plus minus q using either, as I said, parallelogram technique or the tip-to-tail technique. These vectors, when we use vectors, of course, we typically choose a suitable coordinate system, and here we have an xy Cartesian coordinate system, and the Cartesian coordinate system is divided into 4 quadrants: first, second, third, and fourth. It is customary to mention vectors with respect to, if this is vector a, with respect to a positive x-axis. However, it is completely up to you. If you have a vector b, for example, you may choose to define the direction of vector b with respect to, in this case, negative y-axis. If you do that, it's important that you write b is equal to, for example, some units, so it's some magnitude 3 meters, and its direction is 20 degrees sort of left of negative y-axis. Okay, or in this case a is, let's call this 2 meters long and is 30 degrees above positive x-axis. So it is very important to clearly say with respect to which axis you are measuring the direction of the vector. Spell it out so that there is no ambiguity. Now, how to decompose vectors? Vector algebra using vector components. Here we have the dark blue line is vector A, and vector A sits in a xy Cartesian coordinate system. You can decompose vector A into ax, which is the x component of vector A, and ay, which is the y component of vector A. Now the x component is parallel to the x-axis and the y component is parallel to the y-axis. And if the x component, or ax, is pointing in the same direction as the positive of the axis, then ax is a positive vector. And if it's pointing in the negative, away from the positive of the axis, then it's a negative vector. In this example, both ax and ay are positive vectors. So you can write vector A as ax plus ay. Okay, so what you're expressing here is saying that vector A is a vector that has a component parallel to the x-axis with magnitude ax, and a component parallel to the y-axis with magnitude ay. A couple of examples. Here we have vector A, and we know that it has an x component ax, which has a 3 meter magnitude, and a y component which is a 2 meter magnitude. So if you were interested in finding the magnitude of a, well, a squared is equal to 2 squared plus 3 squared. That's using the Pythagorean theorem. So a is equal to 14 square root of 13, I guess, if square root of 13 meters. So that's the magnitude of a. And if you are interested in finding the angle that a makes with respect to the positive x-axis, remember ax is parallel to the x-axis, then we know that tan theta is equal to ay, which is the opposite side, this side here, since this vector here is identical to that vector. Recall that I'd mentioned that you can transfer a vector in space from one location to another, so long as you don't change neither its magnitude nor its direction. The two vectors are identical. And if this is ay, then I can just bring it over here without changing its direction, and that's ay also. So ay over ax, which is 2 over 3, is tan theta, or theta is inverse tan of 2 divided by 3, whatever number that comes out to be. So you can, once you figure that out, then you can say that vector A is a vector which has certain magnitude. We figured out that was square root of 13 meters, and its direction is whatever this number comes out to be with respect to the positive, so that number goes there, positive x-axis. Okay, so now you've clearly defined your vector A. Let me see what I have here. Just a couple more examples. Vector B has a magnitude of 2 meters, but its x component is pointing away from the positive of the x-axis, and its y component is also 2 meters long, but it's a positive number. So bx, vector x, is equal to minus 2 meters, minus because it's pointing away from the x-axis, and by is plus 2 meters. So once again, you can go ahead and figure out the magnitude of B using the Pythagorean theorem, and in this case it's probably best to specify vector B with respect to angle theta with respect to the negative x-axis. So remember, when you come up with your answer, then theta needs to be defined with respect to the negative x-axis. Or alternatively, if you specify it with respect to the positive x-axis, then it's this larger angle here, phi. Here we have vector C, and you can clearly see that it has a negative y component and a positive x component, and you can read off these components right off the chart. As you can see, there's the cx component is 1, 2, 3, 4 units long, and the y component is 3 units long. But as I say, the y component is pointing away from the positive of the axis, therefore it's a negative, it assumes a negative value. If you know the angle, the magnitude of vector A, so this is our vector A, if you know its magnitude, and if you know the angle that it makes, let's say in this case with respect to the positive x-axis, then we can figure out its x component and y components by using the sine and cosine relationships. So we have ax then becomes a cosine of theta, right? And ay is a sine of theta. Once again, this is using the sine and cosine relationships. And it's important to remember that the direction of a vector is not always mentioned with respect to the positive of the x-axis. In this case, the direction of vector C is given by angle phi with respect to the negative y-axis. In a case like this, then ax cx rather. Cx component of C is C sine phi, and cy is negative C cosine phi. Now why cx is positive? Well, cx is positive because the cx component of C is pointing in the positive x direction, and cy is negative because the cy is pointing in the away from the positive of the y-axis. But the main difference between these two scenarios is that notice that here ax is a cosine of the angle, and in this case cx is c sine of the angle. I know it's trivial, but worth mentioning. Don't memorize ax as always being the cosine of the angle, and the y component is always being worked out using the cosine of the or the sine of the angle. It depends on what angle you choose or how you define your triangle here. So do pay attention to your trigonometry. I know it's a trivial point, but a point that is quite often missed, especially under exam pressure. And once again, the magnitude of the resultant vector can be worked out using the Pythagorean theorem. So here's an example. We have vector A, which has a magnitude of 6. In this case, it's an acceleration vector, 6 meters per second squared. And the vector, acceleration vector, makes an angle of 30 degrees with respect to the negative x-axis. So if you're interested in figuring out ax and ay, well, ax, which is this component here, is equal to a, which is the magnitude of a times cosine of 30 degrees. And it's in the negative direction, so we have a negative sign there, and that's equal to minus 6 cosine of 30 degrees, whatever that number is, 30 cosine 0.87. Well, let me just write as cosine of 30 degrees, okay? And ay also is a negative number, and that's a times sine of 30 degrees. Now that I do know. So that's minus 6 times a half. Okay, so that's just a little example to show how you use sines and cosines to work out the components of a vector. And in this figure you see ax and ay shown parallel to the x and y axes respectively. Oops. Sorry about the little mishap there. Okay, let's continue with resolving vector directions. Here I have yet another vector. So by looking at the graph, I don't know the angle that it makes with respect to the x or y axis, but from the graph here I can read off I'm sorry, in this case Vy as being 4 meters per second, and Vx as being 246 minus 6 meters per second. So now I use the Pythagorean theorem to work out the magnitude of V, which is square root of Vx squared plus Vy squared, and that's square root of Vx squared is 36 rather, plus 16, which is square root of 52 meters per second. So that's the magnitude of V, the velocity vector. As for its direction, my first choice of specifying directions with respect to x-axis, but that's not the golden rule, whatever is convenient. So if we were to specify the angle theta here, then we know that tan theta in this case is equal to Vy divided by Vx, which is you take the magnitudes, so don't worry yourself Don't worry about the negative or the positive sign. So long as you know the angle theta that you work out is going to be with respect to the negative x-axis, so long as you spell it out, then you can always quote the angle in between 0 and 90 degrees and not worry about anything greater than 90 degrees. But so long as you spell out what axis it is that you're measuring the angle with respect to. So you're using Pythagorean theorem and the tangent of the angle to figure out both the magnitude and direction of a vector if you know the components of that vector. Okay, now I'd like you to ponder this problem for a little bit. So what are the x and the y? Let me just pause here for a couple of seconds while the phone ringing ends. Yes, it has ended. My apologies. So what are the x and the y components of C? I've shown vector C in blue. So is it A, B, C, or D? If you like to just take a look at the graph. Well, the x component of C is this vector right there. So this is Cx, which is 1, 2, 3, 4 units long, but it's pointing away from the positive x-axis, therefore Cx is equal to -4. And the y component of C is this vector there, which is 1, 2 units long, and it's a positive number, so it's +2. So C is the correct answer in this case. Okay, now let's discuss a different way of decomposing vectors, and this is using unit vectors. Unit vectors I and J. I and J are with no dots, but they have little hats on. I and J are unit vectors. Vector I is in the Cartesian coordinate system. Vector I is a vector which is 1 unit long and points in the direction of the x-axis, or is parallel to the x-axis. And the unit vector I is also 1 unit long and is parallel to unit vector J rather, and is parallel to the y-axis. So if you know that you have a vector A, in this case this blue vector down here, and A, as you can see, is 1, 2, 3 units along the x-axis and 3 units along y-axis, then you can write vector A as 3i plus 3j. That means that my vector A is 3 units long along the x-axis. So remember, I is a unit vector along the x-axis, and J, my vector A, is also 3 units along the y-axis. So vector I can be written in the unit vector language as 3i plus 3j. Now if you also have a vector B, which is this black vector right there, which is 2 units long in actually it's, I'm sorry, the vector B is this green vector down here, which is 2 units long in the I direction and -2 units long in the J direction. So vector B is now written as 2I minus 2J. So if you're interested in A minus B, then you simply add or subtract, in this case, you the I components and also the j components. So to figure out the I component, a minus b is 3 minus 2 I, and which is just 1 I, and the j component is 3 minus 2j, which is 5j. So if you have, let me move to the left here. So if you have a vector a which has a x ax in the I along I direction plus ay in the j direction, and vector b is bx along I plus by along j, then a plus b is simply you sum the x components, okay, and oops, and plus ay plus by along j. So you look at the you sum up the x components to get the x component of the resultant, and you sum the y components to get the y component of the resultant. So actually what I just mentioned up there, I've also tried to show graphically here. You notice that I have two vectors a and b, and I've also shown their respective components ax, ay, and bx, by. If you're interested in the sum of the two vectors, then you add up the x and the y components. This will be the along the I. This is j component, and a minus b, once again that's the I, that's the j component. You can simply add this the components to come up with either the sum or the subtraction of two vectors. Here we have a velocity vector. Another quick question for you guys to think about. Velocity vector which is 100 meters per second due west. Notice that my x-y axis in this case is tilted, not to worry, but it's tilted at 30 degrees with respect to the x-axis. So if I were to ask you to kindly work out the x and y components for my vector v, what would you come up with? So graphically, let's just figure out what the x and the y components are. Well, the x component of v we know is going to be parallel to the x-axis. So here's vx, and the y component is going to be parallel to the y component, of course. That's vy. So vx is a negative number and vy is a positive number. If you know vx is negative and vy is positive, that clearly rules this option out, and this option out, and this option out. So it only leaves these two options to ponder. Now, what is Vx? If this, we've shown the angle with which our Cartesian coordinate system is tilted with respect to north. If that angle is 30, then we know that this angle is 30. Then Vx is equal to V, which is 100 times cosine of 30, and Vy is 100 sine of 30. Actually, Vx also has a negative number because it's pointing away from the positive x-axis. So Vy is is the sine of 30, I know it's a half, so Vy is 50 meters per second. Obviously this is the right solution here. I hope you all got this right. Okay, I'm going to pause for a couple of seconds because there seems to be a little bit of a lag in the software here. So let me pause. Okay, moving forward, let me just mention the ij unit vectors one more time. Once again, the unit vector I is 1 unit long along the x direction, and unit vector j is 1 unit long along the y direction. And here unit vectors I and j are shown. When we I think in a few chapters time we'll also introduce unit vector k, which is along the z direction, so doing three-dimensional analysis, but for the time being we're only going to confine ourselves to two-dimensional analysis. So as you can see in this figure, we have vector a, and vector a is expressed as axi plus ay j, where ax and ay once again are the x and y components of unit vector a. So just a quick example here. If you have your vector v, which is a velocity vector 10 meters per second, and it makes an angle of 40 degrees with respect to the negative x-axis. So if you were to y negative x-axis, because if you were to draw unit vector v starting from the origin, this 40 degrees would be with respect to the negative of the x-axis. So we have we defined our vector v. So what are the x and y components of vector v? Well, the x component is v times cosine of 40 degrees with a negative sign, because vx is pointing away from the x direction, the positive of the x direction, and the y component vy is v times sine of 40, and it's a positive vector, and in both cases v is 10 meters per second. Of course, it's a simple math to calculate the components, so you can now write vector v as minus v cosine of 40 in the I direction and v sine of 40 along in the j direction or the y direction. And to reiterate, if you're doing if you're adding up or subtracting two vectors a and b, where you know the ax ay and bx by, the respective components along the x and the y directions, then simply sum up ax's and ay's to get the respective x and the y components of the resultant vector. Use Pythagorean theorem to get, if you know the component magnitudes, then you use the Pythagorean theorem to get the magnitude of the resultant vector itself, and you use the tangent the tangent of the angle to actually the inverse tan of the y component over x component. So this is, if we have, this is the resultant vector a minus b, let's say that's theta. This is the y component, and this is the x component, of course. So the y component divided by x component is the tangent of angle theta. So you simply use the inverse to figure out what that angle is. So the procedure is that in adding or subtracting vectors, you add or subtract the components, the x components to get the x component of resultant, add or subtract the y components to get the y component of the resultant. Once you figure out the x and the y component of the resultant, then use the Pythagorean theorem to calculate the magnitude of the resultant and use the tangent rule to figure out the direction of the resultant vector. Alright, so here we have vectors a and b. Here's vector a, and here's vector b. And we're interested in calculating both the magnitude and direction of vector c, which is the sum of the two vectors a and b. Well, using the ij notation, a is 100i, and the units are meter, because the graph says so, and we have 0 component along the j. Vector b, we need to figure out the x and the y components, or the ij components of vector b. To do that, you use the sine and cosine identities. So here is bx, and bx is negative 100 cosine of 45 degrees, because this is a 45-degree angle that b makes with respect to the negative x-axis, and that's minus 141 meter. And by, which is this vector right there, is 200 times sine of 45 degrees. 200, by the way, is the magnitude of b, which is plus 141 meters. So minus 141 and plus 141 are the x and y components of vector b respectively. So vector b can now be written in this form: minus 141i plus 141j. So vector c now is to calculate the I component of vector c. Simply, since we are adding up, simply add the two I components of the two vectors. 100 plus minus 141 is minus 141, and to calculate the y component, add the y components together of vector a and b. So that's 141j. So vector c can now be written in the form of minus 41i plus 141j. So the magnitude of vector c itself is then square root, this is using the Pythagorean theorem, square root of minus 41 squared plus 141 squared, which is 147 meters. That's the magnitude of vector c. And if we choose to define vector c using this angle theta in the drawing, this angle theta, i.e. with respect to the negative of the x-axis, then theta becomes inverse tan of 141 divided by 41, which is 74 degrees. So our vector c is 147 meters long and makes an angle of 74 degrees above negative x-axis. Okay, so that's how we define our vector c fully. So yes, you can show a vector either in component form or as its magnitude and direction. Whatever the problem asks for, please pay attention to define the vector in those terms. There are more than one way of defining vectors. And should our xy Cartesian coordinate system be tilted for any reason with respect to, let's say, north, south, or horizontal and vertical, then the I and j are also get tilted. Remember, I always points in the x is parallel to the x-axis, and the unit vector j is always parallel to the y-axis. So our vector c in this case can once again be written as cxi plus cyj. When do we encounter such cases? Well, let's say we have a slope. Slope is the angle theta, and there's a box uh, which is being pulled by some force F. Now it is best to choose our x-axis along the motion of our object, and that defines the y as being perpendicular here, of course, to x. So you can see that the force that we are applying has two components. There's fx and fy, and f then can be written as fxi plus fyj, these two components. Now, where these two components are tilted, of course, with respect to the absolute horizontal and vertical, but it doesn't affect the ij notation, of course. In some cases, we will encounter where we decompose our vector a, which makes an angle with respect to some arbitrary line here. We can decompose our vector a into what we call the parallel component, that's a parallel, and the perpendicular component, a parallel and a perpendicular, by which we mean parallel to that arbitrary line that we had defined and perpendicular to that arbitrary line that we had defined. Sometimes in analyzing forces and fields, we talk in terms of parallel and perpendicular components, so don't be puzzled when you encounter such terminology. It's simply means that we are decomposing our vectors in terms of parallel and perpendicular components to some arbitrary reference level that we care to choose. For example, here we have a force F acting on a surface at an angle which is 20 degrees with respect to that surface. So if that surface is our arbitrary reference level, then we can talk in terms of the perpendicular force to the surface and also the parallel force to the surface, which would be this force here. So you can decompose a vector in terms of parallel and perpendicular components as x and y components using trigonometry relationships. ij terminology is sometimes used, so you can mix and match these forms in performing your vector algebra. It's sometimes easy to make mistakes with respect to when it comes to calculating angles, so do pay particular attention to how you define your angle, with respect to which axis you define your angle. Other than that, this chapter 3 is a fairly simple chapter to read through, so please read through chapter 3 this week, and we'll continue with forces in our next lecture.